Good. All right, everyone. So we're going to continue on. The last thing we had done is we'd done a simple combustion analysis question. And what we're going to find is I'm going to start taking all of these questions here and combining them into kind of one large question. And then after doing that, we'll go through another question that's similar that combines all three parts. So we looked at combustion analysis. And why is combustion analysis useful? It gives you the what? Percent composition. Good, good. At least for some elements, it does. Carbon, hydrogen, and oxygen. Now, what we can do with that information is we can determine the empirical formula. And if we have even more information, we can find the molecular formula. The empirical formula, kind of meaning formula by experiment, is simply going to be the lowest whole number ratio of elements to elements. So what we do is if we know the formula, it's going to be in the lowest possible ratio. You couldn't get it any lower. So for example, if you were to look here at this compound, that has a formula of C10H16Cl4, right? What would be its empirical formula? In other words, what number can I divide all of those by? Yeah, 2 is the largest number that divides into all of those evenly. So I'm going to divide each of those by 2. So C10 would be C5, H16 would be H8, Cl4 would be Cl2. Right? So we can't divide that any lower. Can the empirical and the molecular formula be the same for a compound? Well, let's take a look at a compound. So, for example, here is the Lewis structure of formaldehyde. And if I look at that, what is its molecular formula? Starting with carbon. How many carbons are there? 1. How many hydrogens? 2. And oxygens? 1. Since as soon as you see that any of the elements has a coefficient of 1, you know you can't get it any smaller, right? You're not going to be able to divide the numbers any smaller. Okay, and so in this case, this is also the empirical formula. So the answer is, can they be the same? Yes, they can. And there are many cases where that is so. Can you give me a molecular formula other than this that also has that empirical formula? So a molecular formula other than CH2O that has that formula. So in other words, same empirical formula, different molecular formula. It just has to be, all of these numbers are a multiple of some other number. So, oh, you don't have to give me a name, just give me a formula. You sure, of anything, yeah. It doesn't work. No, okay, so I'm saying different molecular formula, so different number of atoms, same order, but different formula here. Maybe I'm not being clear. Good, C2H4O2. Good. So in other words, I'm just multiplying all of these by 2, or I could multiply by 3, or I could multiply by 20. C20H 40O20. Those would all have that empirical formula, but a different molecular formula, right? Good. Now, the way that we find an empirical formula by combustion analysis is the first thing that we need to do is we have to get the masses of any elements that we have and then convert them into moles. Once we have the moles, what we do is we then come up with a smallest whole number ratio between each of the elements. And when we do that, the element with the smallest number of moles will always be the denominator, as we will see. Otherwise, this won't work well. And then if for some reason the denominators are different, you have to give them the same denominators by finding a lowest common denominator. Now, talking about this is kind of pointless, so it makes more sense to just do this as a problem. So I'm going to continue the problem that we just did, which was a combustion analysis, by taking the data that you were given and using that to calculate the empirical formula. So before I begin, I need the percent carbon, percent hydrogen, and the percent of oxygen from the previous problem. So if some people can remember this for me. So 66.20, 11.18, and what was oxygen? 22.62. Now, percent composition, if you remember, is an intensive property of a compound, meaning it doesn't change at all depending on the mass or the volume of the compound. It doesn't change, okay? Now, step one says we have to convert the masses of each element in the compound to moles. Now, these aren't masses, these are percent compositions. But since this is intensive, you can pick any amount you want. What would be, if you're given the percent composition, always the easiest amount to pick? 100. 100, good. 100 grams. So I'm going to say, assume I have, you don't always have to write this, but I'm going to write it so you have it in the notes. So assume we have 100 grams of this compound. One more time, that's because the amount that you have is irrelevant. Okay, so I'm going to assume I have 100 grams. If I have 100 grams, then how many grams of carbon would I have? 20. Good, exactly, because 66.20% of 100 is 66.20. So for carbon, I have 66.20 grams. For hydrogen, I have 11.18 grams. And oxygen, I have 22.62 grams. Be careful that you don't think that O is a 0. And I need to convert those, as it says in problem 1, to moles. Good. Now, if you wanted to create more work for yourself, you could have picked any other mass. You know, like if you want, just prove that if you'd picked 5 grams, that you can still do this problem. It just adds more steps. You'd have to find out how many grams of carbon you'd have in 5 grams. All right, so let's convert these to moles. And I'm not going to show my work on this because you should be able to do that. How do we convert these to moles? You just divide each by their atomic weight. Good. So if I've got carbon is 66.20, I just divide by 12.01, and that's giving me 5.512 moles. For hydrogen, 11.18 divided by 1.008 would be 11.09 moles. And oxygen, 22.62 divided by 16 gives me 1.414 moles. Now, you will always have one less ratio or one fewer ratio than you have elements. So if I have 3 elements, I will have 2 ratios. I have to pick which element goes in the denominator of all these ratios. And so that's the one with the smallest number of moles. Okay. And so which of these is the smallest number of moles? Oxygen. Good. So what does that mean? Whenever you divide these other numbers by the smallest, that means you're always going to get a number greater than or equal to 1, right? If that's the smallest number, 1.414, anything else you divide by it will be greater than 1. So our ratios are going to be carbon to oxygen and hydrogen to oxygen. Again, these are mole ratios, because that's what your formula is, right? It's a ratio of atoms to atoms, which is also a ratio of moles to moles. Good. So 5.512 moles over 1.414. Oh, and this problem gives not very good results. I should rewrite it. I'm getting about 3.9-ish, which is very close to, this is approximate, right? 4. And how do I write 4 as a fraction? Four over 1, right? Good. We always want to end with a fraction. And for hydrogen, we have 11.09 divided by 1.414. I'll give you about 8. Yeah, this is 7.84, which is about 8, which is 8 to 1. Are the denominators the same? Same digit, yeah, they're 1. If they are not the same, then you would have to do step 3, which was get them all to the same common denominator. So for example, if this had been 8 over 3, 8 over 1, if it had been 8 over 3, then you would have to make this one from 4 over 1 to what over 3? 12 over 3, right? So same value, but different denominator. Good. Now we're going to go in the order that I gave you the elements. So CHO. So what goes after the C? Good. And do you remember doing this in Chem 120? Yeah. Combustion analysis was new. So C4, H, there are 8, because if you look at the fraction, H to O. And then O will be 1. Okay. Now, hopefully it's very clear why the denominator now has to be the same. If the denominators were different, then when you get to this stage, what number would you write down? If it was a 1 here and a 3 here, you'll write down 13, right? Now, you can't do that. You have to come down to the lowest whole number ratio. You can all see the screen, right? I can turn these lights off if it would help. You're fine? Okay, good. Now, I'm only going to give you ratios where the denominator is 1, 2, 3, or 4. I won't give you any others. So let's take a look at some potential examples here. I'll write these out while I talk about them. Oops. All right, good. So if the denominator is 1, then that means, when you do the mole-to-mole ratio, you'll always get something that's close to a number 0.00. So like 3.01, 3.03, 2.99, 2.97. Those are all very close to 3.00, where x could be any number, okay? And so those means the denominators will always be 1. So 3.01, for example, is very close to 3, so that would be 3 over 1. See, I didn't like my last examples because they weren't like 3.01, they were like 2.9 or 2.85, which is a little farther away than I'd like the problems to be. What would you have if the denominator was 2? The decimal would have to end in 0.50, right? Or 0.5. About. These are all very approximate because there's lots of rounding built in. So for example, if I got 2.52, well, that's a lot closer to 0.5 than it is 0.0, right? So 2.52 is the same as, it's almost 2.5, which if you wrote it as a mixed fraction is 2.5, right? And 2.5 written as a, they call this what, an improper fraction? I hate that term. I'm sorry. Improper is better in my view. So it's very proper to me. 5/2. Okay. Is the door, I keep thinking I'm hearing the door, people trying to, well, no, they'd bang harder if they try to get in, wouldn't they? I don't know. I've noticed that when people come to my office hour, frequently I hear, and I'm like, well, that's the thing, but I still can't hear you through the door. I mean, you don't have to, but it's like, ow, anyway, but you get the idea. And I've been saying like a lot today. What, louder, I don't know. It's just been, my hearing's a little off today. Not as bad as my dad. We're constantly yelling at him, get hearing aids, get hearing aids. He doesn't want to hear us though. So I think, my mom has finally realized he just doesn't want to listen to me. So he won't get hearing aids. Anyway, if you get something that ends in about 0.33 or 0.66, 0.67, that would mean that the denominator is probably going to be about 3, right? So 3.67 is 3 2/3, yes? And that would be 8/3. How do you find the numerator here? 3 times 3. Oh, no, this is wrong. Oh, I feel horrid. It's 11/3. Thank you. I'll yell at yesterday's class and blame them. No one saw that. Anyway. And finally, fourths. 1/4, 3/4. You can't do 2/4 because 2/4 is a half. Yeah, good. So anything that ends in about 0.25 or 0.75 would be these. Okay. Now, the reason I put up with these, I make these distinctions is because what if I gave you 3.22? This could be approximately what? 3.25 by the rules I'm giving you, which is 3 1/4 or 13/4. Yeah. But this is also could be very close to 3.20, which is 3 1/5, which is 16/5. So that's why I'm committing to saying I'm only going to pick problems where the denominator is 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. I think there might be one online where the denominator is a 5, but I don't think so. So I will not do this. You'll pick the quarter. These are a few of the questions I can't just make up off the top of my head because I have to find things where the ratios work out. All right, so we all have that? Yeah, okay. Now, to find the molecular formula, you have to know its molar mass, which you could easily find from mass spectrometry. And so mass spectrometry would give you that molar mass, and we can then what we do is we take the molar mass of whatever compound's formula we found, and it must divide evenly into that molar mass. So again, this is easier seen in a calculation versus doing it in words. So the last compound that we saw was C4H8O, right? So the empirical formula is C4H8O, and this has molar mass or molecular weight four times carbon. So 4 times 12.01 plus 8 times hydrogen, 1.008 plus 16 for oxygen gives you 72.10. So this thing called the multiplier is found by just taking the true molecular weight, 288.4, dividing by 72.10, the molecular weight of the empirical formula. And you should get a whole number here. If you're not, that means somewhere you've made a mistake, or something very, very close to a whole number. I got 4 right on the dot. So what you got? Oh, well, pretty much 4. It might be 3.99 or 4.0001. So this means the molecular formula so it's so C4H8, so 4 times 4 is 16. I'm going to write it the long way. You don't have to do this on an exam. Hydrogen, there's 8 of them, right? So we're going to multiply that times 4. And oxygen, there is 1 of them. So we'll multiply that times 4, which is C16, H32O4. Now, in the real world, this is all being done backwards because of the technology we have available to us now. Nowadays, if you have a mass spectrometer and you have a computer, it would tell you everything you needed to know based on that data right there. You wouldn't need the other. The combustion analysis is nowadays used to confirm. So we would work backwards to say this is really the right answer. Because you can do it very, very carefully to a lot of significant digits. And so that's how, if you're going to publish articles saying, I made this compound, here's the evidence I have. One of the pieces of evidence is you send your compound away to a specialty lab that will confirm that this is in fact the right formula. That's not all, but certainly if that formula is wrong, you couldn't have made the chemical you say you have. Okay. Good. But so this is still more of a classical way of approaching it, the way we learned how to do it historically. All right. Now, this example, I've given you a lot of space, right? This example combines all of the last questions. So we have 15 grams of an organic compound that contains only carbon, hydrogen, and oxygen. It's analyzed by combustion analysis, gives you this much water and this much carbon dioxide. Mass spectrometry shows that the compound has this molar mass. What is the molecular formula? So there's a few ways we could approach this, but I want to go through the same approach that I did before. So the combustion analysis will first be used. And what does that give me? Good. So that's going to be the first part of the problem. First, we're going to use the combustion analysis data to find the percent composition. And it's helpful to remember that the percent carbon in CO2 is something, and the percent hydrogen in water is, I think, 11 something something. All right, so we wrote that down a few pages ago. So let's write those numbers down. So what was the percent carbon in CO2? 27.29 and 11.19. Why are those numbers useful? Because what compound do you make in combustion analysis? You make water and carbon. And what's the point of the carbon dioxide? Why is it useful? It tells you the amount of carbon in your original sample. Because remember, when you do combustion analysis, all the carbon in your compound ends up in your mystery compound ends up in the carbon dioxide, and all the hydrogen in that compound ends up in the water. So this will make life easier for us when we're trying to find out how much carbon and hydrogen are actually in the compound. Okay, so let's find carbon. So let's find the mass of carbon. So we have 25.867 grams of CO2. So we just want to find how many grams of that is carbon. So we just multiply by the percent. So for every 100 grams of carbon dioxide, there is 27.29 grams of carbon. Or in other words, you're just taking 25.87 multiplying by 0.2729, right? The decimal form of the percent. 25.867 times 0.2729. And so there's 7.059 grams of carbon in the compound. Just let me turn that off. Wow, lots of spam. That's unfortunate. Okay. Okay, and then we're going to do the same thing for hydrogen. So I had 7.937 grams of water. And multiply that by 0.1119. In other words, 100 grams of water has 11.19 grams of hydrogen. Or I'm getting 0.8882. Yeah. Now I could at this point say that the mass of oxygen is what's left over, right? I'm going to skip that step because I'm just going to go straight to finding the percents, because I can use the same logic. If I find the percent of carbon and the percent of hydrogen, whatever percent is unaccounted for must be oxygen, right? So I'll save myself a step there. Okay, so what is the percent of carbon? You might need to read the problem again, not very detailed, but percent of carbon in the compound is so it's the part over the whole. The part is the 7.059 grams of carbon. What's the whole? That's coming from where? No?
Well, 306 grams.
15 grams.
The 15 grams of the compound. Remember, the carbon is coming from the organic compound. So the part is the carbon, the whole is the organic compound, which is 15 grams. So I'm getting 47.06%. The percent of hydrogen is going to be what? Mm-hmm. 0.8882 grams of hydrogen over, and you know what? Let me get rid of C because that doesn't really make sense. The units don't really cancel. So 0.8882 grams divided by the whole, which is 15 grams. And we multiply that by 100%. And so that gives me a quite small number, 5.921%. And then what's the percent of oxygen? It's just what's left over. So that would be 100% minus the carbon plus the hydrogen. Okay, so 100 minus 47.06 minus 5.921 gives me, I think, 47. What'd you get?
47.019.
Okay. Oh, I see why. I forgot the 5. 47.02, right? Sick digs, guys. Sick digs. Subtracting, that goes to the 0.06 hundredths. This goes to the thousandths. Good. So I now have my 3 percentages. So that was step 1. That's the new thing that we've learned how to do in this class so far. One of them. Step 2 is we want to find the empirical formula. So that's, I think, the first thing we did today, right? So we're going to assume that we have 100 grams of this compound. So if I do, that means I have 47.06 grams of carbon. So 47.06 divided by 12.01, the molar mass of atomic mass of carbon, or atomic weight, is 3.918 moles. Now we need to do that for hydrogen. We have 5.921 grams. So we're going to convert that to moles. 5.921 divided by 1.008 is 5.874 grams. And we need to do that for oxygen. So we have 47.02 grams. sorry, this is my unit is wrong here. This is moles. And so we're going to divide that by what? Very good, 16 off the periodic table. And so that's 2.939. Okay, so we're all clear on this step here, right? I just divided each of these masses by the atomic weight on the periodic table for that element. We now identify the least number on here, and that's again oxygen. Won't always be, although it tends to be pretty often. Okay, so if this is the least, then that means it's going to be the smallest number in the ratios. So the ratios will be carbon to oxygen and then hydrogen to oxygen, correct? So carbon to oxygen is 3.918 to 2.939. Is 1.33, which is what as a fraction? Yeah, 1 1/3 is 4/3, correct? And the other ratio is, hydrogen to oxygen. Good. So hydrogen to oxygen is 5.874. Over 2.939. Which is basically 2, which is a fraction, is 2/1. And now we run into a problem because in the next step, when we go to write the formula, oxygen can't be a 3 and a 1 at the same time, right? So we need to get this to the lowest common denominator here. So 3 and 1, the lowest common denominator is 3. So we'll leave 4/3 alone, and we'll say 2/1 is 6/3. Good. So again, note that we have a common denominator. Good. So now we find the empirical formula. What number goes after carbon? 4. Good. Hydrogen? 6. Oxygen? 3. Okay. And then finally, we want to find the molecular formula. So first we need the molecular weight of the empirical formula. So let's do that. So we've got 12.01 for carbon times 4 plus 1.008 for hydrogen times 6 plus 16 times 3 for oxygen, getting 102.09. And so what were we given, what information were we given about the problem? we were given the mass, right? We were given the mass of water, the mass of carbon, and we were given that it's 306 grams per mole. Yeah. So that's the last piece of information I need. So 306 divided by 102 should be very, very close to a whole number, and it is. It's basically 3, right? Again, if you're getting like 2.7 at that point, that should send warning signals through your mind that you've made a mistake somewhere. But 306 divided by 102.9, 2.97, that's really, really close, right? To 3. 102.09, I'm sorry. Yeah, you're right. I think it was. That we got 306 divided by because I'll put it even closer. 2.997. Yeah. So it's 3. So what is the molecular formula? We're just going to multiply all the subscripts by 3 that are in the empirical formula. So C4 times 3 would be C12. H6 times 3 is H18, and O3 times 3 is 9. So that's my compound. That's still not enough to find out what the compound is, though, right? Because there's probably going to be thousands of compounds. Well, with that configuration, probably not thousands, but tens at least of compounds that have that molecular formula. Yes, that should exist. Sorry. Thinking for a second, going, no, that doesn't exist. No, that should exist. Okay. We all fine? Good. Now, in Chem 120, if you remember your Chem 120, this was chapter 6, except for the combustion analysis, which was kind of new. So everything about moles, that's really been the part that we've been looking for here. Now we're going to move to a preview of what would have been chapter 7, which is chemical reactions and chemical equations. In this class, I am not going to go over balancing chemical equations. Okay, you should know how to do that. If you need practice with balancing equations, there are some in the OWL homework, but under the handout section on the website, if you click on handouts, there's a worksheet for practice balancing equations. So you should go through and do that. I don't always get them perfectly myself, but it does not hurt. Okay, so let's look at some chemical equations here. So it's just the way that we symbolically represent chemical change or a reaction. What we do in a chemical reaction is we begin with one or more reactants. And in a chemical equation, we list them on the left typically. And then we make one or more products that we list on the right. And in between, we put an arrow pointing to the right. So arrow always points towards products. The way we balance a chemical equation is by writing numbers in front of each substance if needed. Those are called coefficients. And we will use those in a number of contexts, particularly when we're looking at mole-to-mole ratios in reactions. And the most important issue about this is that you must have the same number of each type of atom on both sides of the equation. It turns out that you must have also the same total charge. That will be an issue we get into in chapter 4 that makes balancing equations much, much more involved. Starts becoming a 10 to 12 step process. As for right now, since we're not dealing with ions that change their formulas, we don't have to worry about that for right now. Now, it's critically important that you never change the formula itself in this process. So in other words, if you have CH4 in a chemical equation, as part of the balancing, you can't change it to CH6 or CH8. Or you can't change water from H2O to H4O, H408 or something. You can't do that because then you're changing the formula of the compound. Yeah, you're changing the compound. You're changing it to something that it isn't. So you may never do that. Why do we balance equations? We must do this as a consequence of the law of conservation of mass, right? You must end up with the same number of atoms on each side of the equation. So this is a combustion reaction. The darkest circles stand for carbon atoms. The red circles stand for oxygen. And these kind of whitish, bluish ones stand for hydrogen. So what's the name of this? Right here on the left. Yeah, what's its name? Methane. Good. So methane is reacting with oxygen to make carbon dioxide and water. What's wrong with the picture as shown?
There's more than green oxygen on one side. There's hydrogen. Is that the red one?
Red ones are oxygens.
Oh, there's 3 oxygen and 2 oxygen. There's 3 oxygen on the right and 2 oxygen on the left.
Yeah. So there's 2 oxygens on the left, 3 oxygens on the right, which implies you. But more articulately, if you could. It implies that you have magically created an oxygen atom from nowhere, right? So one sprang into existence that didn't exist. What other problem is there? Yeah, 2 hydrogens got lost along the way. So 2 hydrogens got together and turned into an oxygen, which doesn't happen, right? So that's how I would interpret that. 2 of the hydrogens became an oxygen and they all lived happily ever after. And so that is horribly wrong. So we need to work out the ratios so that there's the same number of each type of atom on either side. And this ratio would work. So what this is saying is, yes, there's a methane molecule, but it now needs 2 oxygen molecules. That will give you 1 carbon dioxide molecule and 2 water molecules. And now we can account for each atom on both sides of the equation. In other words, the equation is balanced. Very good. Okay, some general guidelines with chemical equations. We're going to use these, especially starting up in the next lab. It's important to recall that these behave a lot like math equations, with the arrow being a lot like an equal sign symbolically. So first of all, if we remember in algebra, addition is commutative. In other words, x plus y equals y plus x. The order doesn't matter. In chemistry, the same is true for a given equation. So long as you don't move something from one side of the equation to the other, you're okay. So this first equation says 2, don't say AgNO3, what is that? So 2 moles of silver nitrate plus 1 mole of magnesium chloride react to give you 2 moles of silver chloride and a mole of magnesium nitrate. Good. Now, I could have read it the other way. Magnesium chloride reacts with silver nitrate, right? So the way in which I write these is irrelevant. By custom, there's some chemicals I use, I like to, if I'm reacting acids and bases, I always write the acid first. There's no rule saying you have to do it that way. If I'm writing a combustion, I always write whatever's being combusted plus oxygen gives you CO2 plus water. But if you chose to write water plus CO2, that's no less wrong. So we fine on that? Good. You can always multiply or divide each side of a chemical equation by a value. It may no longer appear, though, in a form which is nice. So if I asked you to write this equation here, the combustion of butane, there's really only 2 answers that I would accept. And that's the top one and the bottom one here. So the first version of this has coefficients 2, 13, 8, 10. 13 is a prime number, right? So it has no common divisors other than 1. So this is in the lowest possible ratio. So I want everything to be in the lowest whole number ratio if I can. Now, if I want, though, I could divide everything by 2. And that would give me this balanced equation here. The only issue, though, is that introduces a fraction into the problem. I only make mention of this because later on, when we start getting into thermodynamics and we start saying, how much energy does this produce? For a lot of chemicals, the amount of energy that it takes to burn that is given off when something burns is expressed as per mole, per 1 mole. And so which of these would technically be easier if you're talking about butane, C4H10, if you're saying how much heat is given off per mole? The bottom form, right? Because the top form is for 2 moles, okay? So it means you don't have to take into account the 2 being there. So there will be some times where we have to use fractions, but they are rare. Should we be scared of fractions? No, they are our friends. But if you use those in a calculation, don't write the fraction, write it as a decimal. 13 halves is what? 6.5, 6.5, right? Yeah. Good. And rather than saying atoms to atoms, like we did here, or molecules to molecules, that's really inconvenient. So instead, we're going to say moles most of the time. Now, I can't say grams, right? Because the mass of all of these things is different. The mass of methane is, a mole of methane is different from the mass of a mole of oxygen, etc. So the book gives you this table that shows you all technically the different ways that you could write these. So we'll normally write it the way on the top, but we will understand it as the third way. A mole of CH4 plus 2 moles of oxygen gives you a mole of carbon dioxide and 2 moles of this. Using Avogadro's number, we could break that down into numbers of molecules, and we could break that down further to grams if we wanted to, but we don't write grams in front. But ultimately, you notice if you do convert all this, you get 80 grams of reactants giving you 80 grams of products. Is that what we would expect? Yes. Good. Conservation of mass says that that's what we should get. All right, so if we want to figure out the amounts of products that should be produced in a chemical reaction, or going backwards, if we know the amount of products, figuring out the amount of reactants, we can use the balanced equation to come up with the ratios that everything reacts in or is produced in. So here, for example, is the reaction of aluminum with oxygen gas to make aluminum oxide. I can get from here 6 ratios. For example, I could get for every 4 moles of aluminum, there must be 3 moles of oxygen. For every 4 moles of aluminum that I produce, for every 4 moles of aluminum, that would correspond to 2 moles of aluminum oxide. For every 3 moles of oxygen, that's related to 2 moles of aluminum oxide. And then there's 3 more. They would be the reciprocals of those. Right, so this would be used to convert moles of oxygen to moles of aluminum. The reciprocal would be used to convert moles of aluminum to moles of oxygen, etc. So all this is telling me is, and it's very powerful, I only need to know the amount of one of these to find the corresponding amount of all other chemicals, right? Because I can use the mole ratio. Any questions, any issues with that? No? Okay. So let's do several problems here. And some of these will be very simple, and some of them will get a little more complicated. And I'm going to assign a lot of these for you to do on your own. So using that equation, and I'm going to rewrite it again here. 4 moles of aluminum plus 3 moles of oxygen gives you 2 moles of aluminum oxide. Let's go ahead and look at example 1. How many moles of oxygen are needed to react with 25 moles of aluminum? This is unusually easy but this is a good starting point. If I have 25 moles of aluminum, what ratio do I want? For every 4 moles of aluminum, I will need 3 moles of oxygen. Good. So that's 25 times 3/4, 4.75 is 18.8. 18.75. That's significant digits. Require me to round. Now, in the real world, that's by itself not a very practical problem because we don't have a mole meter in lab, right? We have a balance. So you'd have to convert first from grams to moles, right? Good. And I usually don't want to know the amount of the product. Well, gases, yeah, I might want to know those in moles, but I often want to know them in grams. So same thing, I'd need to use the gram conversions. So example 2 is typical of probably the single most common calculation in all of chemistry. And that is going from the grams of a starting material to the grams of a product or vice versa. It also introduces an important word. How many grams of aluminum oxide are formed when aluminum reacts? First of all, this problem is impossible because I never told you how much. Let's say 50 grams. How many grams of aluminum oxide are formed when 50 grams of aluminum reacts with excess oxygen? So that word excess is so important. It means that there is more than enough, so you don't need to consider it. If I did give you an amount of oxygen, the problem becomes a little more complicated. It then turns into what is called a limiting reactant problem, which we'll talk about next. Okay. So the word excess means ignore the oxygen, only consider the aluminum. So if I have 50 grams of aluminum, we're just going to do very similar to what we did in the last problem. We first need to get it, though, into moles. Yes? So what number do I need here? We're going from grams of aluminum to moles. Good. Yeah, the atomic weight of aluminum is 26.98. Good. So I've got 26.98 grams of aluminum is a mole of aluminum. We're trying to figure out how much aluminum oxide. So we're going to need the mole to mole ratio of aluminum and aluminum oxide. And we see up here it says 4 moles of aluminum make 2 moles of aluminum oxide. And then finally, this line is too big. Let's go ahead and convert moles of aluminum oxide to grams. I think it's 100 and something. So 1 mole of aluminum oxide. So aluminum is 26.98. 2 times 26.98. Right? Yeah. Plus 3 oxygens, that would be 48. So I'm getting 101.96. You notice everything cancels nicely in terms of my units to leave me only with grams of aluminum oxide. Please learn to do the problems this way, okay? Because I'm generally not very generous on a partial credit if I can't very quickly figure out what you did. If you've got numbers all over the place, I'm just going to go, yeah, no, I don't get it, and not partial credit. So what you need to do needs to do it, be written nicely, as close to the style that we're doing it this way. And this is how your textbook does it. It's how every textbook does it. So for chemists to understand it, make sure you write it out in this style. I'm getting 94.5. Is that what you got? Any questions on that? No? All right, so the next section here says I've got 1.5 cyclooctadiene, which is this chemical right here, reacts with 2 equivalents of bromine and makes 1256 tetrabromocyclooctane. Don't you love this? You haven't, that's what organic naming starts looking like. So it gets much more involved. Now that's all ugly. So we don't need this level of detail in these kinds of problems. So instead of using these structural formulas or Lewis structures, let's just rewrite everything as these guys right here. Okay. So I'm going to do example 3, but I will leave the rest for you to do. Wait, we're done at 350, right? Yeah, I think I can do this question. I have time to do this question. All right, so let's start off, first of all, by finding the molecular weight of everything. Because it'll just be easier. So if we have C8H12, C8H12 is 12.01 times 8 plus 16 times 1.00, I'm sorry, not 16, 12 times 1.008. I'm getting 108.18, yes. It may not be apparent, but it would be easier now to go to the last thing. So I'm just going to take, because it's C8H12, right? So I'm going to take that plus add the 4 bromines, which are 79.9. So these are 427.78. And then bromine, I don't count the 2 in the front, right? Molecular weights are just the formulas. So molecular weight of bromine is 79.9 times 2, 159.8. But you agree if I took this number, 108.18, plus 2 times this number, it should give you the same number as this, right? Because you see all the atoms get accounted for. Good. Okay, so that said, so we will say that our starting material here, so we will say spider with double bonds, has this density. how many grams of product are formed if I start with 5 milliliters of that and it reacts with excess bromine. Excess again means I can ignore the bromine. There's more than enough of it. This problem is very, very similar to the last problem. The only difference is instead of starting with grams, I'm starting with, milliliters. Why wouldn't I start with the density, by the way? What's been my advice to you against that? Yeah, don't start with ratios, units that are ratios. The point of those ratios is to act as a conversion factor. Yeah, good. So I'm going to start with the 5 milliliters of crazy double bonded spider, C8H12. And I need to get to moles, but I can't go milliliters to moles, but I can go milliliters to grams. Good. So where am I going to do that? I'm going to say, well, there's 0.882 grams of it for every 1 milliliter, right? So every 1 milliliter of this compound has 0.882 grams. And now I need to get that from grams to moles. So that's why I calculated the molar masses first. There are 108.18 grams of this in a mole. And we're trying to get to grams of the final product. So what do I do here? I say, well, mole to mole ratio. So every mole of the starting material I should have done this the lazy organic chemistry way, which is to call this 1 and call this 2. So we're going moles of 1 to moles of 2, or A, B, right? That would probably be the easier way to do it, but anyway. So in any case, 1 mole of that gives you 1 mole of the final product, C8H12 Br4. And we've already calculated its molar mass, 1 mole of that. And because I'm running out of space, I'll just say is 427.78 grams. And I'm going to leave that to you to calculate, okay? And I would like you to also do example 4 to 6 for Thursday so that I can get ahead right now. Sorry, I rarely let people out early. Because I want to at least talk about limiting reactants. A vitally important subject that I saved for last here, but one of which you should be familiar. Okay. So for right now, I've only asked you to consider one reactant at a time. And if we had another reactant, I've said it was what? In excess, which means we don't have to worry about it. What that means is the chemical I have specified is what's called the limiting reactant. In theory, this is the chemical you will run out of. Okay. Once you run out of it, the reaction cannot go forward. That's what a limiting reactant is. Now, in most reactions, I'm telling you not how much of one reactant there is, but you would want to know the amount of all reactants. And only one of these would generally tell you essentially how much there is of a certain substance. Certain things are almost always almost always in excess. Like, for example, oxygen gas. Why is oxygen gas virtually always in excess? If it's done in the open air, it's in excess because is, yeah, it's limitless. If oxygen gets pulled into your reaction, there's still going to be more. The only time it's not limitless is if you do it in a sealed container, because then eventually the oxygen could run out if no new oxygen can come in to fill the place of the others. There are many, many different ways that we can illustrate the concept of limiting reactants. We can use bicycles, which is, I think, what the textbook does. We can use ice cream sundaes, which is what I do in Chem 120, where I say, well, you need 2 scoops of ice cream plus 1 cherry plus 50 milliliters of chocolate syrup, because we always measure chocolate syrup in milliliters, and that is 1 sundae, right? It doesn't matter if you have 1,000 cherries. If you only have 4 scoops of ice cream, you're only going to get 2 sundaes. Does that make sense?
Yeah.
Good. The cherries are excess. And sandwiches, that's another case. That's what the book does, is sandwiches. Okay, so we're going to look at a very common reaction that comes up a lot in this class. So I am showing the reaction of nitrogen with hydrogen to form ammonia. This is called the Haber process. Anyway, so it even gets a name, it's so famous. Everything I tell you about this reaction this semester is a complete and total lie, okay? We're going to say that 1 mole of nitrogen plus 3 moles of hydrogen gives you 2 moles of ammonia. That never happens. Because we are totally ignoring a critical problem that we will deal with in chapter 13 called equilibrium. This reaction only goes part way and then it gets stuck. And that's true of most reactions. They get stuck. They come to what's called an equilibrium. We are going to go through the lie of saying it doesn't get stuck and it will go all the way to the end. So just, sometimes that might happen and it might take 5 million years, but I don't care if it takes 5 million years, it does eventually happen. So what we're going to say here is, what if you do this as follows? What if I do take 1 mole of nitrogen and 3 moles of hydrogen? Assuming the reaction goes to completion, this is what's called a stoichiometric mixture. That means there technically isn't a limiting reactant because you're using exactly the right ratio, 1 mole to 3. And if the reaction goes to completion, you would get 2 moles of ammonia. What if I used 10 moles of nitrogen and 30 moles of hydrogen? That's stoichiometric because I multiplied both of these by 10 and I should get 20, right? What if I used 50 moles of nitrogen and 3 moles of hydrogen? That's not stoichiometric. That means I'd have a lot of nitrogen left over. Nitrogen is in excess. So let's take a look at a stoichiometric mixture from the textbook. What we're doing here is, so here are all our reactants. This picture is showing what we've done is we've taken all of these and we've circled them so that in every circle there is a nitrogen molecule and 3 hydrogen molecules. And there is nothing left out of any of the circles, right? So this is illustrating a stoichiometric mixture. What this means is at the end, all the hydrogen and all the nitrogen have been converted into ammonia. Agreed? So every circle now has 2 ammonias. And so these are very rare that we do this. This is much more common. So this is not stoichiometric. What this is saying is, okay, we added this, but I wasn't able to find a place for these nitrogens. So we say the nitrogens are in excess, good. And you'll notice that when we go to the circles, each of these circles now has 2 ammonias, but there's still nitrogen left. So if I ask you, what's the total amount of product, you can't just say it's the ammonia, there's still nitrogen. Does the mass of each still remain the same, the total mass? Yeah, good. But you can't say it's just all ammonia. So we would say the N2 is in excess. Okay. Now, we're running out of time here, and that's fine. I'm a little actually behind the other class. But we're going to look at 2 ways of solving these limiting reactant problems, and I will start those on Thursday. We're going to do it the way that we learned in Chem 120, which is you do this problem, grams to grams for both reactants. So for example, if I told you the grams of aluminum and the grams of oxygen, you would do the grams of aluminum and grams of oxygen in a separate problem. And which would be the correct answer? It's always the smallest answer. We all remember that? And the larger answer is junk. It's totally useless. Now, that method works well most of the time. The other method, which most people hate initially, is the BCA table method. The second method is much better when you need to know exactly how much of everything is left over at the end. Does that make sense? So when I need to account for everything, and in Chem 140 especially, that's critically important to know how much there was before and how much of everything there is at the end. And so the BCA table method works much faster for that. It also works much faster when you're dealing with net ionic equations and milliliters and molarity. So I'm going to introduce it on Thursday, but we're not going to make really extensive use of it until starting in chapter 4. Okay, so I'm going to go ahead and we'll end here.